Welcome to this explainer. Today, we're diving into something that honestly might sound a bit dry at first. A 1998 document from the Bureau of Indian Standards called Indian Standard 1161. It's essentially a rulebook for structural steel tubes. But stick with me here, because as we unpack this, you're going to see how the incredibly rigid mathematical rules of manufacturing are literally intertwined with the cultural and democratic ideals of an entire nation. It's absolutely fascinating how the mundane, everyday materials holding up our buildings reflect the exact principles holding up a society.
Before we get into the heavy metal, let's quickly glance at our roadmap. We're going to start with the right to information, decode the standard itself, see how it aligns with global benchmarks, size up some actual steel tubes, and finally look at how all this ties into building a new India. Let's get right to it.
All right, Section 1, the right to information. This really sets the philosophical stage for everything we're about to look at.
We actually kick things off with some ancient wisdom from the Niti Shatakam, a classical Sanskrit text. The quote is, "Knowledge is such a treasure which cannot be stolen." Think about that for a second. It's incredibly striking to open up this highly technical structural engineering manual and be greeted right off the bat by ancient philosophy, right? But it perfectly frames the perspective here. It establishes that the engineering data inside isn't just some closely guarded commercial secret. It's a fundamental treasure that belongs to the people, and it needs to be accessible.
Then we see this brilliant push toward modernization. There's a quote from Jawaharlal Nehru that simply says, "Step out from the old to the new." So we're transitioning from that ancient wisdom straight into modern ambition. The document positions this technical knowledge of steel manufacturing as the literal vehicle for moving the country forward. They're building modern infrastructure while still carrying the philosophical weight of their history.
Now, what's really cool about the context here is that these profound quotes are introducing a public safety standard. You see, this document carries the stamp of India's Right to Information Act. Why? Well, because the Parliament set out to create a practical way for citizens to actually access information controlled by public authorities. By releasing these incredibly strict guidelines on how structural steel is made, it promotes real transparency and accountability. It literally means anyone, anywhere, can look up the exact rules that keep their buildings standing safe and tall.
Moving right along to Section 2, decoding Indian Standard 1161. Let's get into the actual standard itself.
You'll notice this striking visual juxtaposition in the source material. On one hand, you have these beautiful traditional Indian motifs, like an intricately designed Lord Ganesha and the Ashoka Chakra. And they are sitting right alongside highly specific, rigid engineering rules and data tables. It's a really powerful reminder that engineering doesn't just happen in a vacuum. It's produced by a specific culture for a specific people, even while adhering to universal laws of physics.
So what exactly does this document regulate? Well, IS 1161, specifically this fourth revision from 1998, lays down the law on exactly how plain carbon steel tubes have to be manufactured for structural purposes. We're talking about the absolute core framework of construction here. The standard covers a few varieties: hot finished welded, hot finished seamless, and electric resistance welded tubes, which are sometimes called high-frequency induction welded tubes. Essentially, if you're using steel tubes to bear any kind of structural load in India, this document is your ultimate rulebook.
And looking at the timeline, you can see how this standard has evolved. It was first published back in 1958 and then went through a bunch of rapid-fire updates. There was a first revision in 63, a second in 68, a third in 79, before finally arriving at the fourth revision we're looking at from 1998. It just goes to show that structural engineering is a completely living science. As manufacturing gets better, as we understand safety margins more clearly, and as the needs of a rapidly growing nation evolve, the rulebooks have to constantly adapt to keep up.
This constant need for evolution brings us to Section 3, aligning with global standards.
Because, of course, nation building doesn't happen in a bubble. This Indian standard actively aligned its thickness and mass requirements with another standard, IS 1239, but it went even further than that. They actively brought in guidelines from the International Organization for Standardization, specifically ISO/R 336 from 1976, and they also incorporated the British Standards Institution's BS 6323 from 1982. By blending in these global benchmarks, India made absolutely sure its structural tubes were going to be globally compatible. It's a clear recognition that to build a truly modern economy, your most basic building blocks have to speak the exact same mathematical language as the rest of the world.
All right, let's zoom in on Section 4, sizing up steel tubes. This is where we get into the nitty-gritty physical data.
When engineers are working on a project, they can't just call up a supplier and order a generic steel tube. It doesn't work like that. They have to choose from incredibly specific classifications. This standard categorizes tubes into light, medium, or heavy classes, and that's based entirely on the wall thickness of the tube itself. But it doesn't stop there. They are further graded by the material's specific yield stress, using designations like YST 210, 240, and 310. That grading is absolutely crucial because it tells an engineer exactly how much force that specific tube can take before it permanently bends out of shape.
Just take a look at a tiny fraction of Table 1 from the standard. You really get a sense of the massive differences in scale here. Down on the small end, you've got a 15mm nominal bore, light class tube. That one has a 2mm wall thickness and weighs just under a single kilogram per meter. But then, contrast that with a massive 350mm nominal bore, heavy class tube. That beast is 8mm thick and weighs an astonishing 68.6 kilograms for just 1 meter of length. You definitely wouldn't want to drop that on your foot. The full standard maps out dozens and dozens of these variations, detailing internal volumes, external volumes, moment of inertia, radius of gyration. It literally leaves nothing to guesswork.
And because we are talking about structural integrity here, the literal steel keeping the roof over our heads, the public safety mandates are incredibly strict when it comes to manufacturing tolerances. Look at this number right here. For a single light tube, the weight is only allowed to vary by exactly plus 10% or minus 8%. That's it. If a tube rolls off the line and falls outside that incredibly narrow window, it fails. It cannot be used.
And honestly, the physical dimensions are even more precise. For an outside diameter up to 48.3 millimeters, the allowable variance is plus 0.4 millimeters or minus 0.8 millimeters. We are talking about tiny fractions of a millimeter here. Interestingly though, when it comes to the tube's thickness, there actually is no limit on the plus side, meaning sure, make the tube thicker than the standard if you want. But a welded tube absolutely cannot be more than 10% thinner than specified, and a seamless tube can't be more than 12.5% thinner. I love this because it perfectly highlights the safety mindset. You are more than welcome to over-engineer it, but you absolutely cannot under-deliver on the minimum structural requirements.
Finally, let's zoom back out for Section 5, Building a New India, and look at the macro impact of all this. There's a quote in the document from Satyanarayan Gangaram Pitroda that really ties this whole explainer together. He says, "Invent a new India using knowledge." It perfectly links that rigid, uncompromising data about steel weights and millimeter tolerances right back to the ultimate national goal. You don't just build a nation with steel, you build it with accessible, standardized, and reliable knowledge about that steel. And that is exactly why this standard was pushed out to the public. The source explicitly states that publishing this is meant to empower people, especially disadvantaged communities and those pursuing education. By giving them direct access to these safety standards under the right to information, it completely democratizes engineering. It sends a clear message that the rules governing the safety of our shared public spaces aren't locked away in some corporate vault. They are open, they are transparent, and they belong to everyone.
So, as we wrap up today, I want to leave you with a thought. If open access to the exact specifications of a steel tube can help build a more transparent democracy, what other seemingly boring technical data might hold the key to our shared progress? As we've seen, the mundane building blocks of engineering are actually the exact same building blocks of a transparent, accountable society. The knowledge is out there, just waiting to be used. Thanks so much for joining me for this explainer, and remember to keep questioning the structures around you.